Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Digital 2, EET 122. Today we're going to discuss multiplexers, or MUX for short, M-U-X. The symbol for it on the left-hand side. For some reason, your book never has the symbol. I don't know why. But it's like a little trapezoid, shrinking a large number of inputs to one single output. And that's basically what the purpose of a multiplexer is. It's a device that allows several sources in parallel to be routed onto a single line in serial. So that's our single out in serial. And here's our number of multiple inputs in parallel. And you may ask yourself, what is these right there? Well, those right there are the data select. That is telling you which source is going to the output. Okay, so S1, S0. What is X when S1 is 0 and S0 is 0? Well, it's D0. 0, 1, 1, 0, 1, 1. So for all possible combinations of the data select, you get something like this. Okay, so let's say it's 1, 1 on our data select lines. The only thing that's coming to the output is D3. So even though there might be data on D0, D1, or D2, the only thing that's coming out when S1 and S0 or 1 and 1 is D3. So this is the way I like to think about it is D0, that's your dad. D1, that's your mom. D2, that's your digital teacher. And D3 is your best buddy, Johnny Loco. And your dad's telling you to study, your mom's telling you to study, your teacher's telling you to study, but you got your selector switch set to 1, 1, and Johnny Loco's like, dude, let's go smoking cigarettes and fishing down at the lake instead of studying. So doesn't matter that there's data on these threes, on 3D0, D1, D2, you're stuck on D3. But if you rotate your selector switch according to this right here, so right here, let's forget that dumb example I was talking about earlier. And you've got real data coming in the form of D0, D1, D2, and D3. And the data select here goes from 0, 0. So for this first portion, you're going to get D0, 0, 1, that's D1, 1, 0, D2, 1, 1, D3, so on and so forth. D0 for that block of time, D1 for that block of time, D2 for that block of time, D3 for that block of time because it's 1, 1. So what does our output X look like? Well, it's going to be a representation of, in this case, for this first block of time, it's D0, which happens to be, I'm going to draw it in red, 0. Okay, now it's going to grab D1. That is also 0 during this time frame right there. Now it's going to say, okay, grab D2. Well, D2 is also 0 during that time frame. Now it says grab D3. Well, during that time frame, it really is a 1. Okay, now we're back to D0 again, but during this block right there, that's a 0. Now this next one, we're going to grab D1, and that's a 1. Now we're going to grab this next block. That's D2. That's also a 1, so I should not have put that descent right there. And now we're going to back to be D3, and it's taking that 0 right there. Okay, so it's a selector switch. Basically is you are at certain points taking a sample of it. At this point, you're taking a sample of D0, sample of D1, sample of D2, sample of D3, so on and so forth in a repetitive manner. This is time division multiplexing. There's a number of different types of multiplexing out there, frequency division multiplexing, etc., but we're dealing with time division multiplexing. If you just put this on a clock right here, where S0 has a certain frequency and S1 has a certain frequency, it's going to get this repetitive pattern. So this is kind of one of those animals out there that is going to transition us from combinational logic to sequential logic. So remember ET 111? That was the steady state analysis of DC. And then all you guys moved, well, some of you guys moved on to ET 112, and that's time-based analysis of DC. That's what I'd like you guys to start thinking of, is the fact that ET 121 was combinational logic. It's pretty much steady state logic. ET 122 is sequential logic. It's basically time influenced logic. So start thinking about that now. I know a multiplexer can be designed with combinational logic, but it is influenced by time, especially when you have something like this where you can rotate your the data selector. And that's really kind of what it is. It's a data selector. If you think about it, it's just a switch that can rotate up and down. And this guy right here controls what D3 is going to X, or if it's D2 going to X, D1, or D0 going to X. Okay? So the combinational logic for this is, if you think about this, X is going to be equal to D0, D1, D2, or D3, depending upon these guys right here. So for a single combination, X will be equal to Z0 when S0 and S1 are negated. Or it's equal to D1. And when is this guy? Only when S0 is negated. And now we can come up with a full expression right there. So basically what it's saying is, for one and only one combination of these two bits, the data select bits right here, you get this. Okay, so you can come up with a combinational logic function for a multiplexer. So you notice that there was two data select bits. Well, with two data select bits, you get 4 positions. And notice that there was 4 data lines coming in. Coincidence? I think not, as we'll see in the next couple chips here. And the first one is the 74157. That's a quad 2 input mux. Quad because there's 4 of them. 1, 2, 3, 4. 2 inputs. Each of them has 2 inputs, an A input and a B input. Okay, so quad 2 input mux, and just like every multiplexer, single output. And that's the 1Y, 2Y, 3Y, 4Y. And now this has 2 inputs. So 2 inputs only needs 1 data selection bit. So each one of these data select bits is tied to a single data select. Okay, so for a high on that single data select, it's the B inputs go to Y. Low, A goes to Y. Okay. Now there's also an active low enable. And basically, when 0, the chip is enabled. When 1, it's disabled. Okay.